Okay, off we go. So real quick before we get back into the math, I'll just let y'all know. So the grading's actually finished. So we got that done really quickly. And I did not quite have time to finish making the curve. Y'all will recall I put the curve up on the website, and then you take your raw score that you'll get on Gradescope, and then you go to the website and use the curve to translate to what does that actually mean in terms of grades, right? So keep in mind we don't do grades on the 100-point scale in this class. We do grades on the 4-point scale, right? So, what does 67 mean? That doesn't, you got to translate that into the languages of, A, B, C, D, etc. So, by the usual standard A's, I should say the Duke standard also, A is 4, B is 3, etc. Everything should be converted to the 4-point scale, and you should interpret your grade on the 4-point scale. That's all that means anything in terms of how grades are done in this class. So, I didn't get the curve quite done yet this morning. But I will say, and I hope this is possibly good news to everybody in the class, there were no catastrophes. All the grades were pretty decent. Some were excellent. So anyway, if anybody's worried, don't worry. Everything's kind of okay. All right. Okay, so moving along. So, and I should say also, I'm going to finish the curve as soon as I can after class and office hours, and then I have a meeting. But as soon as I possibly can, early afternoon, I think is a very reasonable target. I'll have that curve out to you. We'll have grades published on Gradescope, etc. Okay. All right. So, chain rule. We were talking about the chain rule. And y'all will recall that I'm a big believer in diagrams representing your scenario, such as this one right here. So let's look at this diagram on the left, and notice I've got this function called f that takes x1 and x2 as inputs, it gets y1 and y2 as outputs. Then I've got this function called g, and it takes y1, y2 as inputs and gives z1, z2 as outputs. Now this is what it looks like on a diagram when you compose functions. Okay, and there are various unavoidable consequences when you do this, right? So, in particular, notice the way I have this set up in a diagram. There's no confusion of variables, right? That would be silly. Why would we do that? Don't do that. That's just nonsense. So, no confusion of variables, and the independent variables are in fact truly independent of each other. If I say I want to change x1 but not change x2, yeah, cool, that's fine. Go ahead, no problem. Yeah. And this requirement right here, in fact, let me do it like this. The variables that are the outputs from the first function are the inputs for the second function. Right? So various little observations you can make when you have an actual composition of functions. Yes, you can make a diagram, but that diagram will follow certain rules, right? There are some, just always the case, consequences of what that diagram will look like. So in particular, not every diagram you can draw is actually from a composition of functions. So this is a nice little example here. This is a weirdo little diagram that I've put together, and this is not a composition of two multivariable functions like the diagram on the left is. It doesn't work, right? There's no way it doesn't satisfy those rules. Okay? So now, who cares? Well, the reason we care is because, in fact, this kind of thing will seem to come up sometimes. So, for example, if you look at this example down here, and I've given you various relationships. So, in particular, I've noted how, y1 comes from x1 and x2, and notice that that's sort of represented on the diagram there. And if you just kind of go one equation at a time and just kind of piece things together kind of willy-nilly, right? Just as the equations come to us, then you in fact would get exactly this diagram. This diagram came from this example. Okay. So for what? So what? Who cares? The reason I'm bringing all this up is that you're, in some cases, going to want to apply the chain rule to a situation like this. very often the information that you have that you're trying to work with concerning the various variables that you've got, they're related by various different equations, but they won't necessarily come to you as literally a composition of functions. And the big problem is the chain rule that we have is only for compositions of functions. So our chain rule only applies to diagrams that come from actual compositions of functions. And in a situation where you don't have a composition of functions, we have no chain rule here. We can't apply the chain rule to this diagram because this diagram doesn't represent a composition, and that's all we've got for the chain rule. So we have ourselves a problem. And it's worse than this. It's even worse than I've described. Because if I were to look at this diagram, again, that came from the example we're going to look at in a minute, let me ask the question, reasonable question, what does this mean? Partial of z1 with respect to x1. Well, let me take a whack at it. Right now, this is going to crash and burn, but I think it's instructive to watch this crash and burn. It's tempting to say, well, look, z1 came to me as a function of these variables, x1, y1, and y2. And by the way, coming down to the example, here's that equation. z1 comes to us as a function of those three variables. And so, okay, fine. So z1, we're looking at the partial of z1 with respect to, okay, I'll use orange, with respect to x1, which means I want to let that be a variable, but it's a partial derivative, so that means I hold the other variables constant. I mean, if you just kind of look at it, this would seem to be what we mean by this partial derivative. But this story that I've got now highlighted in this diagram suggests that while I keep track of how much z1 is changing, when x1 is changing, I have to do that while not allowing y1 and y2 to change. But wait a minute, y1 depends on x1. So whether we like it or not, when you start changing x1, y1 and y2 are going to change. You can't say, well, yeah, but I want to pretend that they're not changing. I don't know what that means. Right? This is a problem. It's a real problem. So we should not try to do business with stuff like this. It's not clear what you're talking about, and again, we have to do math in a way that where we at least know what we mean when we write it down. Everybody see the problem? Okay, so I'll tell you first of all what my experience has been. My experience has been that when I've seen work in again back in my past life as a physics major way back when. They know what they're doing. They know how all this stuff works, and they write down equations that are ultimately, I know what they meant when they wrote that, and they know what they meant when they wrote that, and it's kind of okay, but if you really look at it, often sometimes what they write down is really problematic. I mean, it's not clear what they meant as they wrote it down. So I'm going to show you how I fix it. I think this is a reasonable way to fix it. And the big idea is to insert new variables in a way that doesn't actually change anything, but that does allow for viewing it as a composition. And in particular, here's what I'm going to do. I'm going to add a new variable kind of right there. And that will allow me to view these as giving rise to those, which then give rise to color choices. These, and then I have a composition of functions because blue is a function of light green, and dark green is a function of blue. Everything fits. This is fine now. If I introduce this orange variable right here, and we're up at the little orange dot, I introduce a new variable there. Now, no problem. I have an actual composition of functions, and we're good. And then go ahead. go about your business. So, okay, that's wishful thinking. How is it that I can justify introducing a new variable, and doesn't that just kind of change everything? And I say not really, because what I can do in particular is make that new variable actually have the same value as x1. I can just literally, now I can't call it x1 because I need it to be a different variable, so I got to give it a different name. So I'm going to call it x1 star. Call it something. But its whole purpose is to be technically a different variable so that I don't have chain rule problems, but to actually, in terms of its values, to just be x1. And so fine, no problem. And notice the only thing I really have to do then in the equations, I do have to rewrite, let's see here, so this one, where z1 had been a function of x1, y1, and y2, but now, since that's not composition compliant, I just have to make z1 now a function of the new x1 star and y1 and y2. And again, it doesn't really change anything if I turn this into that, because what is this x1 star? Well, it's x1. Right? So this is kind of pulling a fast one, right? And that's perfectly fine, perfectly legal, no problem. And the problems, the fact that the fact that what we had started with was not a composition, I'm not legally allowed to apply the chain rule. Yeah, no more. This is totally a composition. I can totally apply the chain rule, and everything's fine. So with that, before I go on, how are we doing so far? Is everybody buying it? Okay. So, okay, well, off we go then. Now we will just apply the good old regular chain rule. And let's see, we want the partial of z1, which is there, with respect to x1, which is here. And so I have 3 intermediate variables, thus giving me 3 terms. This is just a regular chain rule. Right? 3 intermediate variables, 3 paths, 3 terms. And then, how we compute from that, there is a partial derivative here that's super easy to compute. I mean, don't forget that x1 star is literally just, its value is always the same as x1. So that is always a factor of 1. And a factor of 1 you don't have to write down. And then everything else makes sense. And there's your answer. All of this is highly computable. Partial of z1 with respect to x1 star. No problem. That'll just be 1. Because here's how z1 is a function of these other 3 variables, including x1 star, and partial of that with respect to that. Obviously, 1. Right, and all the other partials are correspondingly convenient, and boom, answer. Everybody good? Now let me tell you what I saw when I was doing all this kind of stuff. What I would see done is they wouldn't make the new diagram, they wouldn't introduce the new variable and thus rewrite, right? Everything would be done straight off of the algebra that had been given, and they would just kind of do like this. Oh, right. They would just write that down immediately. And let me point out how hair pulling out horrifying this is. They're computing one thing by way of a formula that involves another thing that is different, but that they write exactly the same way. That's insane. Am I wrong? Isn't that horrifying? I mean, well, wait a second. If these, I mean, we write the same notation, it'd be so easy to accidentally think they're the same because we wrote them down the same and then cancel them and draw some conclusion. You end up with 1 = 0 probably, something like that. Oh my God, I just think that's outrageous. Anyway, I think this is a much better solution. It's just my opinion. But this certainly keeps track of things for you. Okay. All right. So heads up for this kind of nonsense. By the way, you'll notice I didn't give you any sort of generalized process of, is it true that any diagram that I might be able to come up with, can I introduce new variables and fix it and always get a good diagram to turn out of it? I make no such claim, but I will say that I haven't encountered organically, naturally, going about my business, I have not encountered any counterexamples. So I think this works very well. Okay. Oops. Okay. All right, moving along. Okay, so second derivatives. This is another sort of tricky bit. The way this was shown to me was, again, I'm going to say a little lacking. I felt like it was lacking, and like I was supposed to just keep track of certain things in my head that I found very difficult to keep track of. So I'm going to show you what I think is, again, the easier, better, more careful way to approach these problems. Ultimately, the point is going to be that if z is a function of x and y, then so are its partials. Ultimately, that's going to be the point. Where that's going to show up, I want to, for dramatic purposes, I want to not reveal that just yet. But ultimately, that's going to be the point. So what I'm going to do is just kind of dive in and allow that to come up naturally. So suppose we have some appropriately nice z is a function of x and y. And then also, I'm going to say r and theta are the usual polar coordinates. Now keep in mind, I have this take on polar coordinates that they are the input coordinates to a function. Polar coordinates means how are x and y functions of r and theta, and so in particular, x and y are functions of r and theta. And we know exactly what those glue formulas are, right, from chapter 1. Okay, so we have a composition, and a reasonable question to ask might be, in the composition where z is a function of, among other things, r. Well, if I have this composition, if z is a function of r and theta, what's the partial? But I can also very reasonably ask, what's the second partial? So, okay, let's just kind of start going and see what happens, and then we're going to run into a little bit of a roadblock at some point. But anyway, here we go, taking the partial derivative. First partial, we have two paths because of two intermediate variables, and thus two terms. So that's, old news. That's just regular old chain rule, nothing to it. Not exactly what we're interested in. We're interested in the second partial. So I would just argue that second partial that we're interested in is just the r partial of this r partial that we just computed. R partial of the r partial. That's what a second partial is, right? I mean, is everybody cool so far? Okay. Now, I will real quick point out, this is what the chain rule says immediately, and then I did sort of rewrite things a little bit and make sure you're comfortable with the following. But since I know the formula for x as a function of r and theta, this r partial I can explicitly crank out. Okay, so look up those formulas. Likewise over here, look up and make sure that you're good with those. And then the other thing that I did, it's really just kind of a notational choice, but partial of z with respect to x, I can write it sort of in what you might call Leibniz notation, or I can write it in the subscript kind of Newton-like notation. So again, that's it. Okay. All right, and then, proceeding along, let's see here, r partial of this r partial I've already computed, so there I just plug in. Nothing happened there. That's just plugging in what we already did. And then I find myself with this weird scenario of, okay, let's think it through. I'm taking a partial with respect to r. Partial with respect to r means that theta is a constant. That's what a partial derivative is. So when I take that r partial, that means I got to view theta as a constant. And good news, if theta is a constant, then cosine theta and sine theta are also constants, and so those I can factor out of the expression in sort of the usual way. Okay, now we still haven't gotten to the good part yet, but is everybody kind of still with me? By the way, you won't always get so lucky. By which I mean there is a homework exercise where you will not get this lucky. So in particular, what I say is lucky is, we have this product of two factors here, and one of them happened to be a constant. Isn't that nice? And that's the lucky part. We got lucky here. Very often, neither of the factors will be a constant, and then you'll just product rule. So you just apply the product rule in that place. Okay, now we're ready to address the problem. And that is, what does this mean? Right? If I want to make sense out of partial of zx with respect to r, how am I going to view that? Where is zx? Some people like to think of zx, and this is a reasonable take, at least initially, that zx is kind of represented by this arrow. And so if I want to take its partial with respect to r, okay, well, how am I supposed, I get the idea that the partial derivative of zx is related to this arrow, but how do I take a derivative of that arrow with respect to that variable? We don't have a deal for that. That's not on our list. I don't know. We've never, right? We don't have a move from that. This goes nowhere. This doesn't help us. Here's another thing some people like to do, and that is to rewrite this thing as z, wrong color, as z xr. And I claim that is very, very bad. You can't do that. That doesn't make any sense. That suggests, when you write that suggests that z, again with the wrong tool, that you are viewing z as being a function of a collection of variables including both x and r. Like z is a function of like all of these variables at the same time, because you're saying x and r are both inputs. Well, now your inputs aren't independent. Right? X and y are functions of r and theta. They can't be independent input variables. They're not independent at all. So that's nonsense. It doesn't make any sense. I don't know what that means. Right? Is everybody on board? And again, you got to keep in mind, you don't work for notation. Notation works for you. You've got to make sure that when you write down a notation that it actually means something and actually makes sense, and you can crisply explain exactly what that means. I can't do that with this. It doesn't make any sense. So here's the answer. Here's how we get around this problem. Get around this problem by recognizing, as we noted at the very beginning, z being a function of x and y, so are its partials. So in particular, that means that zx and zy, these are functions of x and y. And if they're functions of x and y, then let's say so. Let's put that on the diagram. Here's my appended diagram. Zx and zy, literally now written as also functions of x and y. put it on the diagram because that's where they go. That is literally what they are. Zx is literally a function of x and y. And all of our problems just disappeared. Just add it to the diagram. Now we can totally make sense out of what this is. That just says, all right, well, partial of, there's Zx. I'm going to take the partial with respect to R. And okay, I've got two intermediate variables. And I apply the chain rule. With those two intermediate variables, that gives me these two terms. There's an x term and a y term. No problem. How we doing? Everybody following? Everybody happy? That's kind of that's the big trick. Everything else is details. I'm going to rewrite some of these things, as we proceed, down in this calculation. Partial of x with respect to r. Well, again, I know that x formula explicitly. That partial derivative is a matter of writing it down. This is just another sort of notational choice. If you want to take a partial of zx with respect to x, well, it's zxx. No concerns. Z is explicitly a function of x and y, and zxx is perfectly well defined, so no problem. And then likewise. And, likewise for the zy partial, right? We've got this thing right here. How do I make sense out of that? Well, zy is there. Partial with respect to r, which is there. I again have two intermediate variables, thus giving me two paths and therefore two terms in the chain. Everybody good? Okay. All right. Couple of bits of advice that I'm going to give on when you're solving problems kind of like this, when you're using the chain rule with second derivatives. One is, don't be in a hurry. Don't try to sort of leap too far in, one step of algebra. That's dangerous. You need to go in smaller steps so you can constantly be keeping an eye on your diagram. Make sure that your diagram represents everything that it needs to. Make sure that you're using your diagram to understand what's a function of what variable and what's an intermediate variable between them, and what should I treat as a constant, because it's always different. And the diagram keeps track for you. So don't go too fast. Have a good diagram and rely on that diagram. And then the big trick, aside from just, be careful, don't forget to supplement your diagram as new things show up in your calculation. So when that happens, that should happen. And then, just go slowly and carefully and watch out for whoopsies. But one of the whoopsies that I like to warn people about is, now I'm going to point out that I used parentheses here, I'm going to say fairly effectively, because with those big parentheses, it's clear that this has turned into that in that step, and then it makes it easier for me to keep track of how this extra factor has to come along for the ride, right? And then likewise on the other side, you'd be surprised how many times I see students making mistakes because they kind of can't read their own writing. And I've been there. I've made mistakes because I couldn't read my own writing. And in retrospect, I feel silly. But you got to kind of take this to heart and don't just kind of jot stuff down, right? Use parentheses, use spacing so that everything lays out nicely so you don't confuse yourself, which again, so easy to do. And a very common mistake that I see. Everybody okay with that? Okay, moving along. Here's a cool application. I think this is a great time to bring this up. So there's this thing called the Laplacian operator. The Laplacian operator is this expression right here. You'll notice it's partial derivatives, second partials, no less. Why do we care about the Laplacian? That's kind of a job for your physics and engineering professors, and that's what their classes are about. That's not really what this class is about. But I will say it's a big deal, and just a real quick, easy persuasion. If you want to understand how waves move or how heat flows or how electrons behave, ultimately you can't do it without understanding the Laplacian operator. So how's that for 3 pretty big deal applications that again, physics and engineering professors can show you how those come up. But the Laplacian operator is how they work ultimately. Okay, so I hope you'll believe me when I say this is a very important object to understand. I claim that this Laplacian, which you'll notice is in rectangular coordinates because x, y, and z, what I'm taking partials with respect to is all rectangular coordinates. I can rewrite that Laplacian, same exact thing, but I can rewrite it in terms of spherical coordinates. You'll notice that all of the variables I'm taking partials with respect to here now are spherical coordinates. Same exact object, right? The Laplacian, still the same thing, but if you want to write it in spherical coordinates, you can. This is what it ends up being. Now, 2 things I'll say. One is, this does not look like a win. Most people look at the choice between these and think, you know what? Thanks, but no thanks on the spherical. I'm going to try to change your minds on that in just a minute. But the first thing I want to talk about is, how can I claim that these 2 things are the same? I claim that these expressions are identical. And the answer is, we're just going to compute some second partials. I should rephrase that. I'm going to point out that hypothetically we could, we're not actually going to do it. For example, compute the second partial of f with respect to theta. And how do you do that? Well, just like on the previous page, f is given as a function of x, y, and z. X, y, and z are functions of rho, phi, and theta in the usual spherical coordinates way for which we have pre-existing formulas. It's just like the polar coordinates example on the previous page. And you can totally compute, for example, this partial here of f, color codes, partial of f with respect to theta using the chain rule and applying appropriately the second derivatives. And it's tedious. And I don't even think I would recommend that you give it a try. It's not that you can't do it. You can totally do it. If you want to prove to yourself that you can do it, it would be a reasonable exercise, but it would be tedious. And it's just a lot of tedium. And I don't want to make y'all or guilt you into doing something that frankly, it's a lot. So instead of having you go through that, I'm going to show you kind of a simpler, kind of morally equivalent computation, and that is back to polar coordinates. Okay. So let me just dive right into this. I'm going to claim that we've already shown this. Now, it doesn't look familiar. Doesn't look like we've done that before. But that's just kind of because of a notational choice. And let me point out that, when I write an operator like this, I write partial with respect to r. What I mean when I say that 2 operators are the same is I mean that when you apply them, you get the same results, no matter what you apply them to. So in particular, what this really means is partial of, whatever function z, let's say, with respect to r is, and just, apply these operators equivalently. And this is literally what we have on the previous page. The r partial of z was trig times x partial, trig times y partial. Literally the very first thing we wrote down in that computation. So we've already done that. Okay, so that's old news, and I'm going to, for convenience, keep using this operator notation. It's convenient. You can put Z's in there if it makes you feel better. It's fine. It means the same thing. So anyway. So a nice exercise, and I encourage you all to do this, is in the same way as we did this on the previous page, do the theta partial. You'll get this. It's an easy exercise. Make sure you can do that. And then I'll just point out that, hey, check it out. The x partial is in both of these equations. And just like you did back in middle school, in a little 2x2 system of equations, you could solve for it. Just eliminating in the usual way. And when you solve for it, you get this formula right here. And that's also very doable, and I encourage you to actually do that yourself. That does not take much time. Make sure you can do that. Okay, altogether, what have we done? Altogether, we started off by taking the polar partials and writing them in terms of rectangular. And then just by solving, we rewrote rectangular in terms of polar. And I claim that's all you have to do up here. Right? We can first write the spherical partials in terms of the rectangular, and then you can just, again, turn it around, solve, and get the rectangular in terms of the spherical. And that's what allows you to rewrite this ultimately rectangular operator in terms of spherical. Just like down here, notice we have polar rectangular operators written in terms of polar instead of rectangular. What I claim you can do up there is write rectangular in terms of spherical. Same strategy, just more details. Okay. Again with the who cares, right? So now I hope you've at least seen sort of what the general strategy is for how to turn this into that. Now let me try to persuade you that this is worth something and that you should care about it. How is this going to affect you? Well, someday you're going to need to compute a Laplacian, either because you're dealing with waves or heat or electrons, I don't know, whatever. Y'all are going to be the engineers. Y'all are going to be the ones doing this stuff, right? So something like that's going to come up at some point. And to compute the Laplacian, you'll have two choices on how to do it. So this is an example of your two options. And in this case, I'm going to look at, let's say, electrons. We'll look at specifically what's called an electric potential. That's voltage, if y'all remember from your E&M stuff. And the function of electric potential has to satisfy this equation. This is called Laplace's equation, and it's just that's how voltage works. Okay, I'm going to need to then take a candidate function, what I claim works, and I'm going to apparently need to be able to take the Laplacian of it, and I better get 0 as my answer is the suggestion here. But in particular, I'm going to have to compute the Laplacian of whatever function I want to entertain as possibly being the right answer. All right, well, here's your options then. You can use the rectangular Laplacian, or you can use the spherical Laplacian. Again, most people choose rectangular at this stage of the sales pitch. But notice, likewise, the function, this is how you write it in rectangular, and this is how you write it in spherical. And now again, a lot of students at this stage would be like, you know what, it's not that bad. I'm going to stick with the rectangular, right? Okay, I guess that's cute, but that's a little bit simpler. But oh my gosh, look at all this horror story down here. This is what I'm scared of, right? Okay. All right, well, let's do these two calculations and see which one stinks the worst. First off, you're going to have to take a z partial of a fraction with a square root in it. You're going to have to use the quotient rule, and then eventually the power rule. And you're going to have fractional exponents, and you're going to have fractional coefficients. And it's just a little annoying to write down. Not that you can't do that. Then you're going to have to take the z partial of that. And then the product rule is going to come up. And then the quotient rule again. And again, blah, blah, blah. There's just a lot that comes up. And then you got to do that 3 more times with the y partial and the x partial. And I've been down this road. Everybody should do this once in your lives. I've done mine. It's not my turn anymore. Now it's your turn. I think it's a healthy exercise to go ahead and crank that out. Again, once in your lives, and then probably never again. Right? And the point being, I want you to experience how inconvenient and unpleasant that is. Okay. It's pretty tedious. Okay. So I'm going to put a frowny face on that. All right, let's look at this one. We'll start with this term here, this operator applying to this function, and oh my gosh, it's trig and fractions, and isn't this bad too? No, this is awesome. Very first thing, I'm going to take the theta partial of a function that doesn't have any thetas in it. That's 0. Instantaneous 0. Right? So, boom, that's gone. No computation even required. That's just a quick observation that, oh, apparently theta partial, there's no thetas, we're done here. Okay, fine, that we got lucky. Fine. What about this second operator applied there? Well, again, the very first thing I got to do apparently is take the phi partial of, oh, yeah, no phis. Okay, so this one's gone too, right? This whole thing, gone. Yeah? That's pretty neat appeal, I gotta say. That's, right? I mean, coming from the perspective of someone who just did this calculation with fractions and square roots and product rule, quotient rule, chain rule, just all over the place. This is a tedious computation. Very little in the way of good luck comes up. A little bit of good luck, but mostly it's just tedious. And with this, I'm already done with this. The 2 scariest terms that I was most afraid of. Poof, gone. Lastly, all right, we're going to do a little bit of work with this one. It's not that bad. A little bit of work. Let's see here. I need a color to choose. I'll use the dark. Okay, so I do have to take a row partial of that, and there are rows in there, and so this is not 0. The row partial, though,
minus k by rho squared.
Yeah, that's right. So it's minus k divided by rho squared. That means that this is minus k, which is a constant, and the row partial of that constant is 0. And this term, again, just disappears mostly in a puff of smoke, right? Okay, we had to do a little bit of work there, but mostly just poof, gone. And with those observations made, we have confirmed, since all of these terms disappeared and became 0, yes, indeed, the answer is 0. And I dragged that out to make sure we were explaining the particular details, etc. I want to make sure everybody sees how quickly that computation works. But in practice, you're like, okay, 0, 0, and okay, 0 partial. I'll give you a 1 over rho squared or something, and then, oh, that makes this a constant, 0, we're done here. It's a 15-second calculation. Okay, so for whatever it's worth, this is one example of many. Okay, but this idea that spherical coordinates is weird and curvy, and I like rectangular. Mistake. You're leaving huge opportunities on the table, right? spherical coordinates in some contexts is the only way to go. It's the best. That's why we do it. We don't do it because we're masochists. We do it because it's awesome. Is everybody cool? Everybody buying it? Okay. All right. So this is a totally awesome calculator. Very powerful tool. It's going to save you tons of trouble. By the way, stuff like this formula, don't memorize it. It's in a book somewhere. You can look it up on Wikipedia, right? It's just freely available in lots of different places. I've never memorized that formula. I would recommend that you memorize that formula. And what we're going to find is that there's actually a lot of mathematical expressions that we're going to be making use of in various different ways that are too many to memorize. And now I do recommend that you memorize the standard Laplacian, right? The fact that the standard Laplacian is this. I mean, it's really easy to memorize. It's the sum of the rectangular second partials. I mean, it's super easy, right? That you should know. But how this looks in spherical, or how this looks in cylindrical, or in 2 dimensions, how does this look in polar? And then, by the way, there's going to be this thing we're going to see eventually called divergence. Okay, well, there's a rectangular divergence and a spherical divergence and a cylindrical and a polar. And then there's this thing called curl, which there's a rectangular curl and a spherical curl. And, oh my God, there's too many different formulas. And you shouldn't memorize the wacky ones. But you should know they exist. You should know where to find them. And you should know how to work with them. Right? So you should, being able to do calculations like this is very important and necessary. Everybody happy? By the way, where did all this come from? Who do we credit? What gets the points for this awesome result? Well, we had to use the second derivative chain rule, right? We had to use second derivative chain rule to derive that formula in the first place. So that's one of many reasons that I think this topic's really important. And side note, I'll remind you, if you look at the content syllabus, it's not in the book. It gets very strange. Anyway, one of my big criticisms of our textbook, which I generally like. I think our book is actually very good overall, but this is a unfortunate omission. Okay, moving along into section 2.6. This is a neat topic. I have a particular way that I like to enter. Oh, I'm sorry, you had a question.
Wait, I'm sorry.
Going back to
the Laplacian. So what exactly is it?
The Laplacian?
Yeah.
Yeah, it's this operator. It's you know how the derivative is this thing called an operator. If you give me a function, then the derivative is something I do to that function, and out comes another function, right? So is the Laplacian. This is something where if you give me an f, give me some function, then I can compute like so, and out comes this other expression. And exactly why and how does this relate to applications is a digression that we don't have time for.
Okay.
But go ahead.
Because the delta sign, so does it
good point. So this looks like a delta, and it is a Greek letter delta, but it's not a change type delta. It's just that there's only so many letters, and sometimes they get recycled. And so this is just a different thing, and you just have context will be your guide as to wait a second, does this mean change, or does this mean Laplacian? Context will usually make it clear, and it's unfortunate. Yeah.
So if we had to use this spherical version, would we be put in it on a test?
Yeah, on a test, I would never write a test question where where my intention is for you to use a spherical Laplacian and then expect you to have memorized it. I would never do that. For this semester, I will not do that. And I don't anticipate doing it in the future, but I don't like to tie my hands. So I'll just say for this semester, I will not do that. I might give you the spherical Laplacian, I might give you a formula sheet in which there are like 50 formulas, and you have to be able to identify, okay, well, yeah, but which one is the circle? You have to be able to go through and identify it correctly, or something like that. But yeah, you don't have to memorize. Yeah.
Great. So, like this, the whole purpose of understanding this was just to see how, like, using the chain rule to convert, like,
that's one of the
spherical coordinates.
That's one of the purposes.
An application.
Well, so this is one example I wanted you to see of how second derivative chain rule is a good thing to be proficient with, because among other things, it gives us awesome tools like this. But the other reason that I wanted to show you this is just it's a cool application of multivariable in general, right? That if you want to understand how heat flows, kind of a big deal, right? Heat's one of the fundamental quantities, physical concepts, objects of study in physics and engineering. Heat is a big one, and if you want to understand how it flows, you're doing Laplacian stuff, whether you like it or not, and this crazy construction here is what it looks like. It's spherical, and is again the big one. So but it was a multi-purpose example. Yeah. Okay, moving along. 2.6. So we're going to make sense out of something called a directional derivative. I like to come at this in a little bit of a weird way, but I think this is ultimately actually really instructive and ultimately really easy. So our book does this in a different way, which is also fine. But I like this one. So I'm going to start by just reminding you what we already know about partial derivatives. So we already know that partial derivatives are the slope of the graph. We already know that partial derivatives are a multiplicative factor. Both of these, of course, with the understanding, when I say it's the slope of the graph, well, yeah, if you look at a tangent plane to the graph, that's in the appropriate direction, in the direction of the variable you're taking the partial with respect to. Of course. And likewise, when we say it's a multiplicative factor, assuming you are actually moving exactly in that direction corresponding to what you're taking the partial with respect to. Yeah. And then I'm going to also claim these two formulas here, and I'm going to call these these are reasonable computations that y'all can do for yourselves. This one is a layup. Y'all can totally correct, because you know the formula for the gradient. You know how to write down standard basis vectors. Y'all know how to do dot products. This is full of mostly zeros. It's an easy dot product, and this partial is what you get. So make double sure that you can do this one 100%. This one over here is a chain rule problem because f is a function of x, y, and z, and what I have in here gives x, y, and z as functions of t. And if you apply the chain rule to taking this composition derivative, write it all down, what you will find is you get exactly this, the partial derivative. So both of those are computations you can do. I think they're both good, healthy exercises. Strongly encourage you to do both of those. And as always, come to me with questions if you have any questions. Happy to help, office hours, what have you. Okay. All right, so partial derivative. I'm going to say 4 things we know about partial derivative. Now, I'm going to pull a little bit of a fast one. All right, so bear with me on this. If the partial is equal to all 4 of these things, then all 4 of these things are equal to each other. Right? That's not a creepy observation, is it? Now I'm going to say it a little bit differently again. This thing that we just made up, right? But what you were going to show is a partial, right? Just another rephrase. This thing is the slope of the graph. This thing is the multiplicative factor, and this thing is computed by that formula. Again, asterisk with the assumption that we're moving in the appropriate directions, right? And so that, we've got to make sure that we use just standard basis vector directions, standard basis vectors in these calculations, in these expressions that we have here. That's all we know, because all we're doing is talking about partial derivatives right now. Everybody cool? I didn't really do anything here. I'm just kind of, instead of viewing these things as properties of partial derivatives, I'm just going to review this as these three things being properties of that expression. For no apparent reason. All right, here's the reason. Yes, this only works for standard basis vectors. But what's a standard basis vector anyway? And I know what you're thinking. Standard basis vector, well, it's very explicit. Standard basis vectors are vectors where the coordinates are mostly zeros with a single one. That's the definition of a standard basis vector. Okay, well, yeah, but vectors define directions. And when you're in the physical world like we are, like I'm walking around in space, right? I am not walking around in an array of numbers. I'm walking around in space. Vectors are a tool for describing actual directions of actual movement. How do we get coordinates out of actual directions anyway? We set up an axis system, right? And so, for example, I can set an axis system like this, and that was pretty arbitrary. Why did I draw the axes like that? There's no law that says I have to draw axes like that, right? Whatever. I mean, you can set up your axes however you want. I could set up my axes like this if I felt like it. You know, maybe wherever it is that I might be tromping around out in the woods, right? And then you can see I've got these level sets drawn, right? Trying to conjure the function we're interested in has got these various level sets. So V appears to be going uphill, for example, right? Which way do I set my axes? Well, north and east are pretty common choices. You don't have to. There might be some natural reason at some point to set up your axes like this. And so now I'm going to ask the rhetorical question, is V a standard basis vector and is W a standard basis vector? Well, the answer is, if you set your axes like this, then V is a standard basis vector and W is not. But if you set your axes like this, then W is a standard basis vector and V is not. So I propose, now given that I can be a free country and all that, I can set up my axes however I want. You can't make me, I can do whatever I want, right? Any unit vector could be a standard basis vector if you just set up your coordinate system the right way. Is that cool? Okay, well, let's come back up here then. I've got this expression here, this weird expression, that I've got here, I'm pointing to, and I say that it's equal to a slope of the graph, and it's a multiplicative factor, and it's computed with a dot product of the gradient, but only if you use a standard basis vector, and then I'm going to return to the point we just made. Yeah, but all unit vectors are standard basis vectors if you look at them right. Now, I'm not saying that I can view partial derivatives in kind of literally any direction, because partial derivatives are defined downstream of having made a choice of coordinates. So, if I want to call it a partial derivative, then I really am kind of stuck, and I have to pick my coordinates first, and then this really does only apply to certain vectors. But I'm just saying, okay, I'm not married to this term partial derivative. So, fooey on that, I have here an expression that applies to any unit vector I want, and it can be interpreted as all three of these things. So I'll just give it a different name. And that's the big idea of what we call directional derivatives. It is just a kind of a rip-off of the idea of partial derivatives. So set up your axes however you like, but for any unit vector, we're going to define this thing called a directional derivative. I'm going to use that notation, call it a directional derivative. Yeah, you got to use a unit vector, but any unit vector that you want, and it's defined by the, whoops, wrong color. It's defined by this formula we have on the previous page, and as we argued on the previous page, it is computed with a dot product with the gradient. It's the slope of the graph as you go in the direction of that unit vector v, and it's a multiplicative factor in the usual way. So this applies for any unit vector. Because again, ultimately, all unit vectors could have been standard basis vectors. Is everybody cool with that? So this is what I call pulling a fast one. Like it seems like I'm cheating. It seems like I have taken something that only applies to standard basis vectors, and now I'm just kind of aggressively, asserting that it also applies to other unit vectors. And I make the observation that no, I'm just observing that all unit vectors truly are, viewed appropriately, standard basis vectors. Okay, all right. So that's the big idea. Directional derivative. Any unit vector works, and pretty neat to be able to say, for example, that if you ask me, hey, what's the slope of the graph in some direction, I can argue as follows. I can say, well, it's a directional derivative, and I've got a handy-dandy formula for how to compute directional derivatives. Dot products are easy. Or if you were to ask me, for whatever reason, what is a certain multiplicative factor? I want to multiply by input changes to get output changes as I go in a certain direction. Oh, yeah. Okay, well, that's also a directional derivative, which I can compute by this handy-dandy formula. So, very cool little trick. Now, I will reveal some algebra here, or some notation, viewed as a multiplicative factor. The thing that you multiply by input changes, right, to get output changes. And let's take a quick pause. When I say input changes and output changes, it could be a discrete movement by some given distance in the given v direction, and the output change is the corresponding change in the value of the function. Or it could be a rate of change, a speed that I'm moving in the appropriate given direction that I want to relate to then the rate of change of the output. It could be either, right? So now let's just talk notation. What do you think would be a reasonable thing, a reasonable notation to put here, the thing that I multiply by ds to get df, the thing that I would multiply by ds dt to get df dt, and yeah, we already have a notation for it. I suppose I could argue that, well, it is, okay, here's my notation. Maybe that's what I should put there. And that's fine, but you know what's really tempting and actually really convenient and satisfying is instead to use this notation right here and to call it df ds. And again, if you just kind of look at the notation, let me try to get this to, there we go. It kind of feels like the ds is canceled. And awkward, it doesn't really, and this isn't really a fraction, and all objections noted, right? But day in and day out, very convenient and satisfying to call it df/ds. So this is a very common notation. You're going to see this a lot. I use this a lot. People know what you mean when you write this. So, good news, you get to use this satisfying notation. Everybody all right? Okay. All right, so let's do some examples. Here you go. Starting this example, we've got a function given, and I want to know what's the slope of the graph of that function when I'm at a certain point and moving in a certain direction. Now that defines a scenario, right? It's kind of like this picture here. I've got some function whose graph I'm looking at, and I am at a certain point and moving in a certain direction, and I want to know what is the slope of that tangent line to that cross section of that graph at the point A and moving in the direction B. How am I going to compute that slope? And we bemoan the fact that, okay, well, I'm not going in the direction of the x-axis and I'm not going in the direction of the y-axis, and slope of a tangent line to a cross section, golly, partial derivative sure would be convenient for this, but I can't because I'm not going in the direction of an axis. So, no problem. Want to know the slope of that graph? Compute the directional derivative. Compute it with this formula right here. And it totally works. Okay. So in particular, here's the computation. Let's see here. Yeah, so we want to compute the slope. Slope from the previous page is computed by directional derivatives. Directional derivatives are computed by this handy-dandy formula. And so all I got to do is compute the gradient. So, all right, you do have to, take your function and take the appropriate partials and then evaluate at the appropriate point, at the appropriate point, you got to plug in. So sure, a little bit of effort you have to go to there, but there's your, there is your gradient, which will simplify like this. The other thing I have to do, coming back up here, do recall, very importantly, that the vector does have to be a unit vector. Let's see, where did I write that? Here we go. Yep, that's got to be a unit vector. Right, so the thing that I dot with the gradient, that has to be a unit vector. That's the deal if I want to make this interpretation. So, okay, well, I wasn't given a unit vector, but no big deal. If you're not given a unit vector, just make it a unit vector by dividing by its own magnitude, like so. What do you think? Everybody following? So, the question says, what's the slope? The previous page tells us slopes of graphs are directional derivatives. It also tells us we can compute directional derivatives with a plug and chug formula, and the rest is literally just chugging. All right. Do be careful of the language, the terminology. It's really easy to mess up as follows. Let me draw a picture of what we've actually got here. We are actually, let's see here. We are at the point 3, 1, let's say is about right there. And we're looking at the vector 3, 4, which is about like that. Right, and then we want specifically to talk about the direction that vector points. That's the unit vector, like that. So that's where our U comes from. Let me show you the mistake that a lot of students will make. A lot of students will misinterpret direction of the vector as toward the point 3, 4, and that is not what it says. Right? This says vector 3, 4. Vectors do not have locations. Vectors are not points. It's not the same thing. Vector doesn't have a location at all. We're not at the point 3, 4 in any sense. Right? 3, 4 is defining a direction. If you misinterpret this as a point, if you think about the 0.3 comma 4, well, the 0.3 comma 4 is about right there. And if you mistakenly interpret as toward the point, then you'll go that way, which is wrong. You'll go in the wrong direction. Right? So heads up, be careful. Don't, as much as we notationally conflate points and vectors for convenience, don't lose sight of the fact that they're not the same thing. And if it says vector, you have to interpret appropriate to what is a vector. And so, like so. Okay, heads up on that. This next example is very plug and chug. Let me just hit the highlights and do something more interesting. So notice the question, various givens, and it asks for DTDS. It asks for rate of change with respect to distance. And remember from the previous page, let me try to get this all on the screen. Rate of change with respect to distance means the multiplicative factor that is the directional derivative. So again, this question here is just literally asking us to compute the directional derivative, and we compute directional derivatives with dot product with the gradient again. And again, further details, now make sure you can do that. You should absolutely follow through these details. Make sure you can do the algebra. Make sure you can compute this gradient appropriately. I did some little convenient creative plugging in, factoring and such. Right? So make sure you're good with that. And let me get on to the last thing on this page. An awkward terminological confusion. This unit vector requirement. Now, for what we're doing and in this course, the fact that the vector has to be a unit vector is important to know what we did, right? The whole idea is we were sort of piggybacking off of the idea of a partial derivative and partial derivatives. That's all in terms of unit vectors. It's just unit vectors. If you want to be able to make all the interpretations that we just did, unit vectors only. Okay, here's the thing though. It's still a perfectly reasonable question to ask. Hey, suppose I'm moving with some velocity in the domain. This could be any vector. This is still a reasonable thing to want to know. How fast the function's changing? Yeah, still a reasonable thing to want to know. Still a reasonable thing to talk about. And by the way, as it turns out, this is another thing you can confirm, still computed by this same formula. So if you remove this unit vector requirement, you're still talking about something interesting, and it's still computed by a convenient formula. You just don't get properties 1 and 2 anymore. So let me go back to this page. If you define, let's see here, let me do it like this. If you have the unit vector requirement, right, then directional derivative denoted like so, defined with that formula, computed with that expression, and it's a slope and it's a factor. But if you remove that requirement, let me do it like this. If you say any vector, I can still call that a directional derivative. I mean, again, free country and all. I mean, now that's not consistent with how we're going to use the term directional derivative, but I'm just saying outside of Math219, people can use whatever terms they want, and a lot of people will still call this the directional derivative. They'll use the same notation. They will compute it perfectly correctly with this same expression, and the only cost is it's no longer a slope and it's no longer a multiplicative factor. So this definite source of confusion when you get outside of this class. To emphasize, in this class, we will assume unit vector. Let's see what colors. Unit vector, and therefore all of this. In Math219, that's what directional derivative means. But again, outside of Math219, you will see certain situations where for non-unit vectors, they'll use that term, that notation, these formulas. And very often, the people that use this term differently than we are will not announce themselves. And I have actually experienced extremely knowledgeable and qualified, professional, leading researchers not even realize that there was a different way to do it, because they've always done it a particular way, and why would they do it any different way? And they just always do it the same way, and they didn't even know that you were assuming something differently. Right? So I'm sorry to say, you have to be on the lookout for this. Right? So, let's say it differently. Everyone should be on the lookout for this. If you're working with somebody and they say, hey, yeah, and so, directional derivative, blah, 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 your ears should perk up. You should think, oh, wait a minute. Is he one of those guys? Right? Or is he one of us? Which way, what did he mean when he said directional derivative? And you got to worry about that. Right? And again, the world will not resolve this problem for you. So anyway, heads up. By the way, just so you know, outside of Math219, I'm one of those guys. I personally think this makes more sense like this, and I'm willing to sacrifice these to pay for it. Outside of Math219. So this is not a bad idea. This is just a different way of thinking about things. Okay, all right. So we are therefore done with that, whatever page that is. I can't read it, and we'll pick up here tomorrow. See y'all later. And again, I will have grades out to you, exam grades out to you by let's say the middle of the afternoon. I should comfortably be able to do that. And good job. Again, no catastrophes. Everything was fine. And generally speaking, the grades were I'll say a little higher than I was expecting. So great job with everything overall. All right. See ya.
Are you